Welcome back. Today we will explore functions with an eye towards creating ones that have nice computational properties. In a previous video, we explored how to use the equation f of x equals b to explain some nice computational qualities of various types of functions. We singled out three special kinds. An injective function was a function where f of x equals b always has at most one solution. Maybe some solutions won't exist. Surjective functions, on the other hand, will always have a solution to f of x equals b, but they may have more than one. And bijective functions are the special case where f of x equals b always has exactly one solution. Together, these three form the strongest form of computationally relevant functions. You can check out our previous videos to learn more about these functions and their properties. Unfortunately, most functions we encounter today do not have any of these qualities, but we won't let that discourage us. Instead, today we'll study ways to start manufacturing new functions from those we are given, which do have some of these qualities. We'll get started by exploring how to create an injective function from a given function f. To explore the idea, we begin at a bike shop. Our bike shop inspects bikes and makes an estimate for repairs. If a client accepts the estimate, the shop writes the order, charges the client, and gathers the order into the client's personal folder. After that, the folder gets filed in the filing cabinet. It's old school, but why mess with a classic? Now let's stand back and understand the process. The overall function w has just been factored into a composition of two functions. First, the charge function c. Then, the filing function, which we call f. As an equation, we can write w equals fc. That's what this commutative diagram is showing us. Two paths to the same place are hiding an equation. Notice we've left out the composition symbol, the tiny circle, between our f and the c. The reason is, well, because we're grown-ups. This will be a common notation going forward. The little circle c is what's meant by putting these together like multiplication. Now, the same customer can visit the shop several times with different repairs, so there can be many work orders in one folder for the client. But the shop better not file two different clients as the same person. The filing function, therefore, must be injective. One client, one folder. That is, f of x equals b has at most one solution. Knowing this property of filing, we should now look to exploit this in our software design. Designing our data type, we begin with diagrams. We form our types based on the context ctx that has a function f mapping from a to b. We call this new type image of f, denoted im of f for short. Recall our formation rule is written in sequence, a universal programming language, but you probably want to choose a language you can program on an actual computer today. One style might be in the spirit of C++, Java, Scala, and many other languages, where you use keywords like class, def, and return, and surround content in parentheses, brackets, and braces, like f of x. In another style, such as Haskell, Idris, and OCaml, we use keywords like data, where, and let. And here, spaces and indentation replace most uses of brackets, similar to how we write sign of x without parentheses. Next in our diagram, we connect our a and b to our newly created image type. We start from a and map into image, thus creating our first introduction rule for the image type. There's no standard notation, but some people like to add im as a superscript to f, perhaps with a bar which reads induced onto the image of f. Once more, sequence give us a universal program for the introduction, also called a constructor. Software conventions on creating constructors vary, but I'll use descriptive names like store. Once more, we illustrate the syntax in two different ways. One focuses on the elements to move around, and the other focuses on the function's type. Both are adequate. Next, we connect our image back to B by creating an elimination rule from our new data type image of f into B. We'll come back to the hook on this arrow in a moment. It's a reminder to exploit the injective law. Once more, we turn to sequence to translate our diagrams into a program, a universal program. We then pick a programming language and make whatever alterations are needed to make the sequence into that language. Finally, it's time for a computation rule. The diagram here is not very exciting. All we need to add is that this diagram commutes. That is, any two paths to the same point are equal. This hidden equation is now precisely the rule that tells us what our program must do. Keep in mind, computation rules are only skeletal. You can engineer this in many useful ways, addressing the concerns you know to be important. At minimum, you will need to decide if you want to use lazy evaluation, where you wait to see if a computation is used, or eager, where you pre-compute as soon as possible to save work later. In between is a host of clever ideas that you will have to pick from. Now that we have a complete data type for our image, it's time to consider how to exploit the injectivity. So far, we haven't used that at all. There are many ways we can exploit injectivity, but for this demonstration, I want to exploit the version that says every injective function f from a to b has a left inverse. You can watch our video on injectivity to learn more about this property, and in particular, I want to recall the introduction of our use of partial functions. These are functions in which not every input necessarily has an output in the targeted codomain. We put a question mark next to it saying maybe as a possible output. Programmers may also know this as a maybe or option monad, but we won't be using the monad properties, just the idea of having the possibility to return an error. Now we want to start by extending our diagrams in order to locate where the left inverse belongs. Drawing our f from a to b and our existing image type, we add a reverse arrow of our injective function. This is now a new introduction rule. Notice the arrow ends at our data type image. So we should copy down the associated sequence for that introduction rule. We can also convert this to pseudocode. Let's use just one this time. Notice the formation hasn't changed, so we still have the same class. We have the same introduction rules as before, and the elimination rule hasn't changed either. However, we now add one further introduction, this new arrow. I'm treating this like adding a further function instead of a new constructor, hence the keyword def, but you can design this differently if you like. Now recall that for every introduction rule and every elimination rule, we need to have a computation rule pairing them together. Since we've produced 2 introduction rules and only 1 elimination rule, that means we need to have 2 computation rules. So let's add the missing computation rule. We get this from the diagram. Where does it commute? Where are the hidden equations? We designed the left inverse to be the left inverse of the injective function. Therefore, if we apply them together, we should get back to the identity. That is, if we try to invert the restore function, we should return to the place in the image that we started with. To make this in software, you need to be somewhat clever. One option is to make a new algorithm that literally reverses our restore function. For example, in the bike shop, such a function could be to search the cabinet for the folder we are looking for. Many functions have a naturally describable algorithm for the left inverse. But sometimes that extra work can be avoided if we have better data types. One thing we might be able to do is create an implicit context in which we add to the existing data. Imagine that whenever we have data U that comes through our image, we add a small mark to it, like a label that says made in this case, made in this image. That tells future users that the data came through our image. In some programming languages, this can be done with what's known as a mix-in or an implicit, or possibly a subtype. And you can search for these behaviors online. Continuing with the eager example, we would add a trait, that is the made in tag. When we create the data at the beginning, we add the keyword with, which tells our program to mix in the new trait, the made in tag. Now later when we need to invert the reverse command, it already has been made in the right place. We simply search for the made in tag. If we find it, we can return it to where it was made. Otherwise, we raise an error, knowing full well that it could not have come through our particular constructor. Now a proper left inverse or a clever data type may not be available to you at every situation. And if you only have the injective property, don't give up. You can still use this to create a unit test. That is, a runtime test to see if your code works properly. Give it different inputs and verify that this always comes out with different outputs. This may be costly and you may not be able to exhaust all the possible inputs, but check values on the boundaries and a few suspicious possible inputs to see if it at least pass some of your testing. At the end of the day, nothing stops you from writing a proof down in the documentation to remind yourself and anyone else who has to deal with your code that this does in fact exploit the injective property. We now have a strong data type ready to exploit the injective property. All that's left is to make it universal. It's time for an upgrade at the bike shop. Recall that the owners took the bicycles and wanted to file the work orders. They did this in 2 steps. Charge the client, add the file to the folder, then file the folder in the filing cabinet. As an abstract process, W equals FC means that the total work order process is the composition of a charge with a filing. Now it's time to digitize records, but without losing the old system as a backup. The owners purchased a computer, and charges are now being entered directly into the computer in a digital form. As a backup, the owner prints out the client files and files them in the cabinet, but only once in a while. This lets the owner build trust in the new system before saying goodbye to the paper trail. After several months, the owner is convinced that W equals PD. That is, work orders digitized then printed is the same as the old system, work equaling to filing after charging. Not only that, printing the records only files one folder per client. It remains injective. So, it's finally time to migrate. Having planned ahead, the old paper system can be digitized. Standing back, we see the full lifespan. The paper method was in fact a universal program. It only broke down the work function providing an injective filing system. It was able to transfer the process to the next technology, hence universal. In time, there may not be a need to keep paper files at all, and we might replace the work function with a digital command that stores everything in a file system. The new injection will replace the word print with the word save. Save to will be injective, and this will make a new image function. And how do we migrate? This is where the power of injectivity comes in the most strongest. Suppose that our injectivity is supported by a left inverse. Then, starting from our image, we apply the injective function to go from the image back to our codomain B. Then, we use the left inverse for the alternative solution. This reverses the injectivity from the alternative to the same codomain and allows us to migrate our data through their channels. Of course, there may be situations where a migration function comes to mind right away, but having the access to a left inverse is enough to guarantee this process. So it's a win for us. Fast forward to the present, and the files will need to be migrated to a cloud. The design won't be bothered. It was universal from the start. It is ready to migrate by design. The use of images guarantees that the useful properties of injective functions are available to your program, but without having to start with an injective function at the beginning. And if you can do this with injective, then chances are that you can do something like this with surjective and possibly even bijective. But that will need to wait until next time. That's how you take care of your chalkboard.